Welcome back to the course of chemical crystallography. In the previous lectures, we have learned how the structure solution programs work, and we discussed about the different methods of structure solution, like how does direct method work and how a Patterson method works. So today we will start with the structure refinement. So what happens is that when we get a data, what we have is a set of HKL reflections with the corresponding intensity and sigma of I. And this is a long list, as you already know, depending on what kind of crystal it is and what kind of unit cell you have. This list can contain number of reflections starting from about 2000 to even 3 lakh, depending on the size of the lattice, the amount of data you have collected, up to what to theta and so on. So in a data structure solution program, what is done is first these reflections are arranged in decreasing order of their corresponding mod E values. Based on that, the strongest to weakest is arranged, and based on that, the top some 300 to 400 reflections are selected with very large E values, and their corresponding phases are guessed. Of course, by applying mathematical interpretation, applying logic, maybe doing symbolic addition method, or by doing Patterson synthesis, we assign the phases, and then with those guessed phases for various FHKLs, we do the corresponding Fourier transformation to get the row XYZ for all the possible atoms that are present in the unit cell. Remember, this FHKL is sometimes also written as FO. It is also sometimes just written as simple F observed. So this is the observed structure factor with the guessed value of phases, and it is used in the structure solution program for the Fourier transformation method. So by doing this rho XYZ Fourier transform of FHKL to rho XYZ, what we get is a partial structure. So this partial structure sometimes is complete for a simple molecule. For a complicated molecule, it may only lead to the main molecule or a part of a molecule, or molecule without solvent. So whatever we get in this initial structure solution method is then used as a structure model. From this model structure, where we know a large number of XYZ, so XJ, YJ, ZJ values for say about 20 atoms. If the structure is about 30 atom structure, and we know the positions of about 20 atoms from this initial structure solution method, we take those 20 coordinates corresponding row xj, yj Zj are then known, because now we know what atom is at what location. So from this rho value, we then do a reverse Fourier transformation or inverse Fourier transformation to get the new values of FHKL, which we call as the calculated structure factor from the structure model. In some textbooks, in some documents, in manuals, etc., this is simply written as FC. So we get a large number of structure factors calculated from the electron densities that we have got in the initial structure, and then we try to compare this calculated structure factor with the observed structure factor, and we find that of course there is a difference. So the difference is FO minus FC. This can be positive, this can be negative as well. When this FO minus FC is positive, that means the model is still not complete. There must be something still to be assigned so that the structure factor amplitude should match the observed value, which generally never matches 100%, but this difference can be minimized. When it is negative, that means whatever atom we have placed there is incorrect. It probably has a less number of electrons, or its occupancy is less, which increases the calculated structure factor compared to the observed structure factor. So these observations are then made during the structure refinement process. So what we have is, I write it once again here, we have a large set of F observed HKL. We do a Fourier transformation to get a set of rho Xj, Yj, Zj, which gives me the starting model. So from that we get the correct rho Xj, Yj, Zj, that is, now we have assigned the atoms, carbon, nitrogen, oxygen, whatever atoms are there based on our chemical knowledge. And then after assigning those atoms, we again do a Fourier transformation in this row to get the F calculated HKL for all the reflections that we have in the .HKL file. So then we of course take the difference, F observed, modulus of F observed minus modulus of F calculated. So we write it as mod of delta F, and we try to minimize this difference. That means we try to minimize the difference between the calculated structure factor and observed structure factor. That means we try to reach the correct structure based on this method, and this is done in a repeated fashion. So from these values of delta F, we again go back and calculate the new coordinates of the atoms. In this process, we may get more atoms which were not seen in the previous plot. So we may be able to identify the solvents, we may be able to identify some disordered parts. So once we have done all that and our molecule, the desired molecule, suppose is something like that, is visible, and the atoms' bond connectivities are reasonable, what we at this point have are corresponding x, y, z coordinates for all these atoms, their occupancy, and isotropic thermal parameter. So at this point we have x1, y1, z1. Normally the occupancy parameter is 1. In shell X it is written as 11.000, and isotropic thermal parameter is something like 0.0342, whatever. So these quantities are now refinable quantities for every atom. So 1, 2, 3, 4 and 5. If the occupancy is fixed, that is here it is 11, this means it is fixed. In that case, this parameter reduces to 4. So now, if there are about 18 atoms like this, here how many we have? So we have 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17, 18 such atoms. Remember, I am only counting non-hydrogen atoms. So we have 18 non-hydrogen atoms. And we have total 4 parameters to be defined at the moment. And these are isotropic thermal parameters, so this is a spherical representation of an atom. And then when we allow the anisotropic parameters to be defined, this thermal parameter changes to 6 numbers which represent the atom in an elliptical fashion. So it defines the ellipse around the nucleus, and this elliptical representation indicates the electron density distribution around that particular atom. If the ellipsoid is large, it probably indicates that the molecule has a large thermal vibration, and it may indicate that the molecule is disordered. It may also indicate that there is inappropriate identification of the molecule. So a large thermal parameter may mean a number of different things. So at this point, when we do this anisotropic refinement, what happens is that all the atoms are converted to ellipsoids, and a parameter called R factor, which we all now need to learn, starts to be reducing. When we have a data, we see one parameter called Rint. I think we have discussed about this in one of the previous lectures. So Rint is nothing but FO square minus FO mean square, the mod and the sum of all those terms divided by the sum of FO square. The another term, which is the R sigma, this is equal to the sum over of standard deviations of F observed square divided by sum of F observed square. These two parameters are related to the quality of data, and as I indicated, they should be less than 0.1 to be qualified as a very good quality data. The other parameters that we need to look at during this structural refinement are the parameters R1, which is now you will be able to understand that it is again sum over FO minus FC by sum over all the FOs. That means this parameter would keep this parameter would be reducing during the structure refinement process. What happens in a refinement process is that the FCs are calculated again and again based on calculated repeatedly based on improvement in the structure or structural parameters. I mean to say that during refinement process, the Xj, Yj, Zj are refined for all the atoms. Also, the isotropic thermal parameter, the V value, is also refined for all the atoms. So, as this structure factor Fc is a function of both the coordinate and the thermal parameter of that atom, at every step the Fc for every HKl gets modified, and then we compare it with the observed structure factor. So the difference between observed and calculated keeps on reducing. So as a result, this parameter continues to reduce. Here also, this R1 should be less than 0.1 to be acceptable for a publishable data. In addition to this R1, we also keep an eye on another parameter called the weighted R factor, or WR2, which is nothing but this sum over weighted FO square minus FC square whole square of that divided by sum of weighted FO square whole square of that, where this parameter W is equal to 1 by sigma of FO square whole square plus AP square, AP whole square plus BP, where P is equal to 2FC square plus max FO square comma 0 by 3, and A and B are constants for a particular data. So this parameter is also going to be reduced continuously, because this contains FO square minus FC square in the numerator, and this quantity keeps on reducing as and when you improve the model. So a general relation between R1 and WR2 is generally WR2 is about 3 times the value of R1. This is a very crude relationship between these two quantities. The other parameter which we also look at is called the goodness of fit, or generally written as GOOF, also represented as S, which is nothing but another quantity which has ideal value as 1. So it is calculated as W into FO square minus FC square, the whole square of that by N minus P and square root of the entire term. So S for ideal structure solution is 1.000. Here N is equal to number of reflections and P is number of refinable parameters. So during this structure refinement process, we keep an eye on all these parameters and try to reduce or minimize these parameters, or in case of GOOF, we try to make it close to 1 by making appropriate corrections and alterations during the structure refinement process. So the interest here is always to identify the atoms correctly, assign them appropriate occupancies, and refine it a few cycles. When again and again I am saying refining, it is linear least square of refinement. Linear least squares refinement method is used for the structural refinement. During this process, it modifies or alters the atom coordinates to fit the electron density appropriately and to also keep the bond lengths and bond angles appropriate as per the chemical bond connectivity. So this refinement process leads slowly towards the complete structure. Let us see one example of the structure solution and refinement using OLEX2. Here OLEX2 is a package which I will explain in another a video where we will use another data and we will talk about how to carry out the disorder and all that. Here during this short presentation on structure solution using direct methods and then refinement, I will quickly go through this process. What you can see on the window is the first step after structure solution, which leads to some electron density peaks. You can see there are some brown colored peaks which are unidentified. This is a result of a structure solution program where the phases were gauged and the rows have been calculated using the Fourier transform from the gauged structure factors. The amplitudes are real, phases are gauged, phases are gauged. So from that it gives us something like this. We can see there are some brown spheres with a brighter intensity and some of them are of weaker intensity or feeble spots. So those are of very low electron density and the others are high electron density. So we can remove the low ones by scrolling and we have only a part of our molecule. So now let us assume that we don't know what the molecule is. As a chemist, for me it looks like a benzene ring. So we can assign these as carbons. Maybe as I know it may be all carbon, I just assign all of them as carbons. Of course, it is possible that all of them are carbon, it is possible that some of them are not carbon, maybe nitrogen or oxygen or whatever. So, I have assigned them as carbons. This is the step where the unknown electron density is assigned as a particular atom. So, now the structure refinement program knows what atom I have assigned, what should be the number of electrons in that, and from that it can calculate the structure factor FCs, and it will immediately tell us what is wrong in this. So, now we go to the refinement part, and again we use shell XL and structure least squares method. We use 10 cycles of refinements, and we are saying that you find 20 more new electron density peaks, although I know that this structure does not have any other atom other than these which are already in the screen. So, if I click refine, you will see in the background it has done a refinement and it has given us more brown peaks which at the moment are meaningless. So, after removal of those brown peaks, what we can physically see is that these two atoms are looking very small compared to rest of it. Why? Because those are incorrectly assigned. Here, in these two cases, these two atoms are smaller than the assigned. It means that it has a larger electron density than what it actually has been assigned. So, let us assign it as fluorines and we do the refinement. See, now the weighing parameter has come, the W parameter has come here and it is red. We have the goodness of fit parameter coming here. The R factor is 21%, WR2 is 58%, the R int is 6.2, I by sigma is 18, average I by sigma, that is the intensity upon standard deviation, and the goodness of fit is 4.083, which is far away from 1. So, the structure is far away from the correct complete structure. So, now again we do a refinement, it does least square refinements. Now, what it shows that the atoms have come of nearly same size of the carbon. Now, what we see is again this particular atom has a much smaller thermal parameter compared to its neighbor. If you put this cursor on this, what we can see is that the U iso value, which is here in the third line, U iso is 0.02. This U iso for that atom is 0.009. So, that indicates that this particular atom is also wrongly assigned and could be something which is slightly larger than carbon. So, we change it to nitrogen, and also we notice that R factor has reduced from 21 to 12, WR2 also has reduced, goodness of fit has improved. So, we tick this weighing scheme which should be refined at every step. So, now when we refine, things are much better. You see that R factor has come down to 12%, goodness of fit is 1.5, the shift, which is the shift per standard deviation during the refinement cycle, is also close to 0. So, if I look at these atoms in terms of their coordinates, what we see are these are the fractional coordinates x by a, y by b, z by c. This parameter 11 indicates that the atoms are all occupancy 1. Then this parameter indicates the isotropic thermal parameter. So, this isotropic thermal parameter for all the light atoms are very similar. You can see that these are 0.26, 20, 18, 18, 02 and so on. So, now it says here Z is 0.5. What does it mean? It means that this particular compound is solved in such a way that only the half of the molecule is present in the asymmetric unit. In P21 by C space group, the asymmetric unit has half molecule, means the total unit cell will have 4 asymmetric units, that is 2 molecules. So let us see then how that symmetry is generating this molecule. So from mode we go to symmetry and grow, and it shows that the molecule is going to grow in this direction, and we make it becomes like that. So this is the entire molecule that we have in the lattice, but only the half of it is appearing in the asymmetric unit because the center of inversion of the lattice is matching with the center of inversion of this molecule. So we do a few rounds of refinement to see if the R factor further reduces. If it does not, then we do anisotropic refinement on all the atoms. So if we do anisotropic refinement, you just click anis, it incorporates one command and transfers all the thermal parameters to ellipsoids, as you can see here. These atoms which are now shown are no longer sphere, but they are like ellipsoids, right? What we see here is now that the R factor has reduced to about 10%, WR2 is 36, and what we have is goodness of fit is 1.4, which clearly indicates that the structure is very close to its real value. What we need now is the hydrogens. It is important that we discuss the treatment of hydrogen at this point, which I will also discuss in a later stage in more detail. These hydrogens which are sort of appearing here from the electron density map, you can see there are some hydrogens appearing here, but not all of them are appearing because hydrogen is the smallest element in the periodic table with the minimum electron density that is possible. So locating the hydrogen atom from X-ray data is nearly impossible. So we do not try to locate those hydrogens, rather we try to fix them geometrically at their ideal locations. So when we say add hydrogen, it simply adds those hydrogen atoms and immediately refines a few cycles. And what we see here is now the R factor has reduced to about 8%, WR2 is 30%, which is about the 3 times, nearly 4 times in this case, and the structure is nearly complete with goodness of fit is 1.15. So if we do a few rounds of refinement, it may improve these parameters. If it does not, we need to look at the intensity statistics. We need to see if there are some reflections where the FO and FC calculation is still very much different. So this list here on the right gives you a large list of molecules, a large list of HKLs where the difference between FO minus FC is large. So these are the error per standard deviation in the calculation of FOFC. So if we reduce this number to about 6 and click on omit, so it then omits those reflections which have slightly larger deviation than acceptable from the refinement cycles hereafter. So we just do a few rounds of refinement on this structure. Now we see that after removing or eliminating those reflections from the refinement cycle, remember we are not removing that reflection from the HKL file. The refinement software will not consider those reflections during the refinement process. It has reduced the R factor to a value of 4.6 and WR to about 15%, and the goodness of fit is now 0.99, which is very, very close to 1. So this completes the refinement of this particular structure, and you can see everything is green. So when everything is green, it indicates that the structure refinement is complete and things are have gone in right direction. So in this today's lecture, I have shown you how the structure refinement can be done both theoretically and also with the data. So with this, we conclude the portion on single crystal X-ray diffraction, how the data is collected, how the structure solution is done, and how a refinement is completed. In next couple of lectures, we will be going through an instrumental demonstration, how the crystal is mounted and things like that, and then we will have a complete discussion using OLEX2, how structure solution and refinement is gone, and also we will discuss about the disorder in a molecule. So we conclude today's lecture with the note that we must look at structural parameters at the end and make sure that all of them are green and nothing is glowing as red.